Cache is asked in almost every senior interview. It looks deceptively simple until you try to make both get and put O of 1, and suddenly the data structure choice is the whole problem. Get this one cold, Bookemondrus. Fixed capacity, get a value by key in O of 1. Put a key value pair in O of 1. When full, evict the entry that hasn't been accessed the longest. Confirm extensions before designing. TTL per entry, thread safety, distributed caching. Know which problem you're solving before you start building. Here's the insight that unlocks the problem. You need O of 1 lookup. That's a hash map. You need O of 1 ordering. Move any element to the front, remove the last. That's a doubly linked list. Neither structure alone does both. Together, they do. The hash map stores key to node. The doubly linked list maintains recency order. Head is MRU, tail is LRU. On get, look up the node, move it to head. O of 1. On put, create a node, add to head, store in map. If over capacity, remove the tail and remove it from the map. O of 1. Every operation, constant time. One implementation detail worth explicitly mentioning. Sentinel Nodes. A dummy head and dummy tail that never hold real data. Without them, every insert and remove at the boundaries needs null checks. Is head null? Is tail null? With Sentinel's head.next is always the MRU node, tail.prev is always the LRU. And every pointer operation is uniform. No special cases, no boundary bugs. 4 pointer primitives build everything else. Add to head, wire the new node between head and head.next. Remove node, wire its neighbors directly to each other. Move to head, remove node, then add to head. Remove tail, remove node on tail.prev, and return it. Every cache operation composes these 4. The elegance is in the composition, not in any individual piece. Thread safety follow-up, synchronized wraps everything simply and correctly. Reentrant read-write lock signals intent more clearly. But here's the catch that surprises people. Get mutates too. It moves a node to the head, so get needs a write lock. Both operations serialize anyway. For high-scale systems, shard the cache into n independent caches by key hash. Each shard has its own lock. Contention drops by a factor of n. Mention this as an extension. It shows systems thinking. Know the Java shortcut, linked hashmap with access order true, override remove eldest entry to return size greater than capacity. LRU cache in 5 lines. Mention it, then implement the hashmap plus doubly linked list version anyway. The shortcut shows you know the library. The manual version shows you understand the data structure. Interviewers want both. TTL extension. Wrap each value in an expiring value record with the value and an expiration timestamp. On get, check if current time exceeds expiration. If so, remove and return null. Background eviction is harder, a scheduled thread or a priority queue ordered by expiration. Call out the trade-off. Lazy eviction on access is simple. Background eviction is efficient for memory pressure. Let the interviewer direct you. Draw the hashmap plus doubly linked list diagram first. Label head as MRU, tail as LRU. Walk through a put, a get, and an eviction before writing code. 4 things to hit. Why hashmap plus DLL, why Sentinel Nodes, thread safety trade-offs, and the linked hashmap shortcut. Cover all 4 and you've answered the whole question. 2 structures, 4 pointer operations, 1 elegant composition. LRU cache is a pure data structures problem dressed as a design question, and when you understand it at that level, the implementation writes itself.